Imagine throwing a tennis ball at a wall, and instead of bouncing back, it just passes straight through to the other side. Sounds impossible, right? Well, three scientists just won a Nobel Prize for proving that this exact thing happens in the real world. In 2025, the Nobel Prize in Physics went to John Clarke, Michel Devoret, and John Martinis for doing something that sounds like science fiction. They took quantum tunneling, this weird phenomenon where particles ghost through solid barriers, and proved it doesn't just happen at the tiny atomic level. They showed it can happen in circuits big enough to hold in your hand. And this discovery? It's the foundation of quantum computers that Google and IBM are building right now. Let's start with what we're used to. You kick a soccer ball against a wall, it bounces back. In our everyday world, objects can't pass through barriers unless they have enough energy to break through. This is classical physics. But down at the quantum level, the rules completely change. Back in 1926, physicist Erwin Schrödinger figured out something mind-blowing. Particles aren't just tiny balls bouncing around, they also behave like waves. And these waves don't just stop at barriers, they spread out and extend into regions where the particle shouldn't be able to go. When a quantum particle hits a barrier that's too high to cross normally, its wave function doesn't just vanish, it extends through the barrier. On the other side, there's a small but real probability that the particle will appear there, as if it tunneled straight through. This isn't magic, it's been measured and verified thousands of times. Nuclear fusion in the sun only works because of quantum tunneling. Protons need to fuse together to create energy, but they repel each other. They don't have enough energy to overcome this repulsion normally, but quantum tunneling lets them slip through the energy barrier. Without tunneling, the sun wouldn't shine. Radioactive decay happens because of tunneling. Alpha particles get trapped inside radioactive atoms but occasionally tunnel through and escape, which is what we detect as radiation. Flash memory in your phone, that works because of quantum tunneling. Quantum sensors that detect tiny magnetic fields, also tunneling. This phenomenon isn't abstract, it's in your pocket right now. For decades, physicists accepted that quantum tunneling was real, but they assumed it only happened at microscopic scales. Atoms? Sure. Electrons? Absolutely. But anything bigger? No way. Quantum effects are fragile. They get destroyed by heat and vibrations. So naturally, scientists thought macroscopic objects couldn't possibly show quantum behavior like tunneling. The question became, is there a hard boundary between the quantum world and the classical world? Or can quantum mechanics apply to bigger objects under the right conditions? In the 1980s at UC Berkeley, Clarke, Devoret, and Martinis built an electrical circuit using superconductors, materials that conduct electricity with zero resistance when cooled to near absolute zero. Inside this circuit, they placed a Josephson junction, which is two superconductors separated by an incredibly thin insulating layer. When cooled, billions of electron pairs called Cooper pairs started moving together, acting as if they were a single quantum particle. If they could show this macroscopic system could tunnel through an energy barrier, they'd prove quantum tunneling isn't limited to the microscopic world. They cooled their system down and started measuring. What they saw was stunning. The electrical state of the circuit would suddenly jump from one configuration to another, not gradually, but abruptly. A voltage would suddenly appear, marking the moment the system had tunneled through the energy barrier. They also found the energy was quantized, changing only in discrete steps like a staircase instead of a ramp. This is a hallmark of quantum mechanics. The temperatures were so low that thermal energy couldn't explain what they were seeing. The only explanation was quantum tunneling. Their measurements matched quantum theory's predictions perfectly. They had proven that a macroscopic object big enough to hold could behave like a quantum particle and tunnel through barriers. Those Josephson junctions they used, they're the building blocks of superconducting qubits, which companies like Google and IBM use to build quantum computers. A qubit can be in a superposition of both 0 and 1 at once, thanks to quantum mechanics. And the ability to control quantum tunneling in these circuits is what makes qubits work. Quantum computers could solve problems that would take regular computers thousands of years. Drug discovery, cryptography, artificial intelligence, All could be revolutionized by quantum computing, and it traces back to understanding quantum tunneling at macroscopic scales. Quantum tunneling has been a recurring theme in Nobel Prizes over the past 50 years. This 2025 prize is special because it pushed the boundary from microscopic to macroscopic, proving quantum mechanics isn't just for atoms. This research also enables quantum sensors that detect incredibly weak magnetic fields used in medical imaging and brain studies. There are implications for secure communication too. Quantum systems can create channels that reveal any attempt to intercept them. What Clarke, Devoret, and Martinis really did was bridge the gap between two worlds physicists thought were separate. The quantum world where everything is weird and probabilistic, and the classical world where things behave predictably. They showed that with the right conditions, you can bring quantum behavior into the macroscopic realm. You can engineer quantum effects in objects you can touch. Quantum tunneling went from being a theoretical curiosity to an engineered reality. Scientists can now build devices that deliberately use macroscopic quantum tunneling to do useful work. The 2025 Nobel Prize recognized 3 scientists who proved that the bizarre laws of quantum mechanics aren't confined to atoms. They can be brought into our world, scaled up, controlled, and used to build the technologies of tomorrow. Reality is way weirder than we thought. Subscribe for more such videos and click on bell icon to get updated.